Here are solutions to homework set number 15 for ECE 111. This homework set looks at solving problems in Matlab that you're going to encounter when you take Signals and Systems. Now, Signals and Systems is a course where we look at analyzing circuits and filters. One of the topics is called Fourier transforms. Now, when you take Signals and Systems, you'll be analyzing Fourier transforms by hand. One of the beauties of Matlab is even if you haven't had Signals and Systems yet, I can solve those problems using numerical techniques in Matlab. That's one of the things that makes Matlab so powerful. So this is one of the typical problems that you'll see in Signals. I have an input to a filter that looks like so. It's periodic, but it's not a sine wave. Now, sine waves we like because if I have a sine wave input, I can use phasors. If I have a filter, I can find the output of the filter using phasor analysis. Well, what happens if the input is not a sine wave? That's what this problem's all about. That's what Fourier transforms are all about. So this is the first problem. Given that waveform, come up with a curve fit. So basically you can curve fit anything. In Matlab, what you do is if I want to solve n equations and unknowns, or if I have more equations than unknowns, I use least squares curve fitting. So in this case, if I want to do a curve fit, here's x of t. Come up with a polynomial curve fit with 6 unknowns. To do that, I set up the basis function. So here's the basis. That's just 1 t squared, t cubed. I want to solve for my unknowns. And to do that, that's least squares. That's something we've covered several times in this course. So doing that, I'll just see how much of x fits onto this basis. And when I do that, I get 6 numbers. What that means is this number is times 1 times t squared, t cubed, and so on. If I plot the two together, plot t versus your data in blue, t versus the curve fit. B times a is my basis, 1 t squared, t cubed, times a. So it's 0.28 times 1 minus 0.57 times t. There's my curve fit. Plot the curve fit in red. And what you get is here's the data in blue, there's the curve fit in red. That's a curve fit. So basically you can curve fit anything. If I add more and more terms, I'll get better and better. However, this is not a useful basis because with phasors, I know what to do with sinusoidal inputs. This is not a sinusoidal input. It's a curve fit, but it's not terribly useful. Leads to problem number 2. Okay, so let's change the basis and make it something useful. Instead of using a power series, let's use a bunch of sines and cosines. The reason being is previously we looked at phasors and superposition. If I have a linear system, what a linear system means is that f of a plus b plus c is f of a plus f of b plus f of c. If I can express x in this form, then what happens when x goes through a filter, I don't know. But what happens if a bunch of sine waves go through a filter? That I do know. I use superposition and treat that as separate problems. When the input is DC, find the output using phasors. When the input is 1 radian per second, find the output using phasors. Likewise at 2 and 3 radians per second. So one way to find the coefficients is to use least squares curve fitting. So here's my basis, 1 cosine, sine, cosine 2t, sine 2t, and so on. Do least squares curve fit, I get a bunch of numbers. It's just a curve fit. If I plot the two together, t versus x, t versus a curve fit, it looks a little bit better. If I added more and more terms, it'd match even better and better. So in terms of problem 1 versus number 2, it's just a curve fit. Which one's better? Really hard to say. But in terms of what happens when I run this through a filter, this is much superior because now my basis is a bunch of sine waves. I like sine waves. If the input is a bunch of sine waves, I know what to do. I can use superposition and phasors to find the output. So that's problem number 2. Problem number 3 says, suppose y is related to x by a differential equation, where basically there's a filter. Find y, well, eventually we want to find y of t. Well, one way to do that is if x is this waveform, it's not a sine wave, I got a problem. So split up x in terms of sines and cosines. One way to do that is to do least squares curve fitting. Here's my basis function, do least squares. A second equivalent way of doing that is to use Fourier transforms. So a more efficient way of finding the terms is called a Fourier series expansion. It uses the property that sines and cosines are orthogonal. If this is x of t and I find the average of cosine over period is 0. Average of sine over period is 0. If I take the average, all these terms go to 0, I just get a. So one way to find the constant term is just take the average, or mean of x, that's a. Same thing we got before. To find the cosine term, what I can do is take this function and multiply by cosine of t. And take the average. Now the average of cosine times a is 0. This goes away. All sine waves are orthogonal. The average of sine times cosine is 0. Cosine 2t times t is 0. All these terms average out to 0. The only term that's not 0 is cosine squared. The average of cosine squared is a half. So to clear out the half, I multiply by 2. There's the cosine term. Likewise, multiply by sine, I pull off this term, times a half. Cosine 2t, sine 2t, and so on. This is another way of finding exactly the same answer. So problem 3 is identical to problem number 2, just a different way of doing it. The thing to note is when you do a Fourier series expansion, expanding terms of sine waves, it's just curve fitting. I've got a bunch of data. I don't like the form of it, so let's do a curve fit. Curve fit with a bunch of sine waves. So again, not a whole lot different than problem number 2. The reason I did that is problem number 4. Suppose I've got x and y are related by a filter. X is not a sine wave, find y of t. Well, what I can do, again, is use superposition. What superposition says that if I have a linear system, then f of a plus b plus c, I can split it up. Now, from the previous problem, I've got x of t, that's this periodic waveform that's not a sine wave. I can split it up into 4 terms. The DC term, 1 radian per second, 2 and 3 radians per second. Treat that as 4 separate problems. Find the output at 0, at 1, at 2, and 3 radians per second. Add up the answers, I get the total answer. So doing that, starting out at DC with s equals 0, this is the gain everywhere. The input at s equals 0 was a0. That's back over here. That's my constant term. Output is gain times input. So here's the gain. Find the gain at s equals 0 times the input at x equals 0. I get y of t. There's the first term. That's a. For the second term, when s equals j1, here's the input. It's a1 times cosine plus b1 times sine. In phasors, the real part's cosine minus j is sine. So there's the phasor representation of my sine wave at 1 radian per second. S is j1. Here's the gain everywhere. That's the gain at 1 radian per second times the input 1 radian per second gives you a complex number. What that means is real part's cosine minus j is sine. So that is the answer at 1 radian per second. At 2 radians per second, here's the frequency, here's the input, cosine and sine. Here's the gain everywhere. Find the gain at s equals j2 times the input of j2 gives you the output. Real part's cosine minus j is sine. At 3 radians per second, here's the input. Here's the gain times input. Real part's cosine minus j is sine. Okay, once you're all done, I can use superposition. I've got y of t at 3, 2, 1, and 0 radians per second. Add them all up, I have the total answer. So here's the total answer. DC plus 1 plus 2 plus 3. Plot them. Here's the input. There's the output. Now this is really the power of phasors and Fourier transforms. Given any periodic input, I can approximate it with a bunch of sine waves. I like sine waves. I know what to do with sine waves. With sine waves, I can use phasors. With phasors, the output is gain times input. You're going to need to use complex numbers, but if you don't mind complex numbers, it's pretty straightforward. Add them all up, I get the total answer. That's really the power. Any complex or any periodic input I can solve this way. And that's part of the reason that we're covering sine waves, phasors, superposition, because that really opens up what you can do. I can solve for any periodic input. Now, one caveat. With Fourier series, in theory, I have to go out to infinity. If I go back to problem number 2, that's not a great approximation. Here's problem number 2. That's not a great approximation. I need more and more terms. So in theory, I have to go out to infinity. Well, an infinite number of terms is kind of a pain to work with. Fortunately, you don't really need to go out to infinity. But look at the answer. I can do a pretty good job just approximating this with 2 terms. There's the DC term and the first harmonic. And I can see that at the output. The output, the red line, is almost a pure sine wave with a DC offset. So a pretty good approximation is to assume all these terms are 0. And the reason for that is most signals, most X's, contain primarily low frequency terms. My filters typically are low-pass filters. They pass low frequencies, block high frequencies. Put the two together, the high frequencies tend to get filtered out. And that's what you're going to do in electronics fairly often. I want to come up with a good idea what the output is. To find out what it really is, throw it in Circuit Lab, or build it. To approximate it, I'm going to do a pretty good job. Just look at the DC term, look at the first harmonic, ignore everything else. And I'm going to come up with a pretty good estimate what the output is. It's a little bit wrong, but it's going to be close. When you get closer, add more terms. That's a whole lot of work. Or throw it in Circuit Lab. But just using the first term, the DC term, and the first harmonic gets you pretty darn close. And that's really common in electronics. In electronics, I do things like if I have a PWM signal, that's pulse width modulation. If this is my input going through a filter, find the output. But what you'll do in electronics is say, let's approximate this with a DC term, that's the average, and a sine wave. I know the frequency, I know the amplitude peak to peak. If that's my DC term and first harmonic, find the output. Little bit wrong, but close. And oftentimes in engineering, I just want to get close. If I want to get closer, then I need to add more terms in Fourier series or throw it in Circuit Lab. So that's homework number 15. The point behind it, again, for the Fourier series, if it's a little bit confusing, don't worry. You'll get that for 5 or 6 weeks when you take signals and systems. For now, the point is using Matlab. Using Matlab, I can solve a large number of problems, including curve fitting for periodic inputs, including finding the output when the input is a sine wave. That's complex numbers. Matlab is really, really powerful. Knowing very little about what you'll be taking when you get to signals and systems, I can solve these problems in Matlab. So that is homework set number 15 for ECE 111. And again, the point is using Matlab in this class. You'll see it again when you take signals. The first time's always the hardest. So hopefully when you get to signals and systems and you look at Fourier series, you'll kind of remember here's what we did previously, and hopefully it makes better sense the second time you see it. Homework set number 15.